I'd like to welcome Dr. Yvette Cendes and her husband, Flores. There, I remember it. Welcome to both of you. Thank you for coming all the way down from Harvard CFA to talk to us. As you can see, Dr. Cendes is going to be talking about cosmic explosions from supernova to tidal disruption events. And it's a little hard for me to see. Dr. Cendes is a postdoctoral fellow at the Center for Astrophysics, Harvard and Smithsonian, where she specializes in transient radio astronomy. She's written for several publications, including Astronomy, and in the December meeting, December issue, she has this article with this lovely illustration, How to Swallow a Star. So if anybody's ever wanted to learn about how to swallow a star, this is going to tell you exactly how to do it, right?
Well, the talk will tell you too.
Well, the talk will tell us, oh good, we get to hear some of that. So you've written for Astronomy, Discover, and Scientific American, and currently you're the astronomy consultant for the Guinness World Records. And additionally, you're known as Andromeda 321 on Reddit. And the astronomer here comments are read by millions around the world. So we're very lucky that you come here to the couple of dozen people when you could actually talk to millions. So I don't want to drone on any longer. I know you're all here to listen to this talk. So welcome to everybody here. Welcome to everybody online. And let's make sure that your speaker works for you first.
All right, we have everyone. So yes, so as I said, this is my first public lecture, and I'm going to tell you guys about what I usually do all day when it's a working day, which is study transient events in radio astronomy. Specifically, giant space explosions is going to be the focus of the talk tonight. So I'm going to focus on two specific giant space explosions, supernovae, which are when very massive stars explode at the end of their lives, and also tidal disruption events, which is when a black hole has a star wander too close to it and it shreds the star apart. I'm going to tell you a bit about how these things happen, why we study them in radio. I'm even going to tell you guys about stuff I've been doing just in the past few weeks because it's very exciting, so I couldn't really restrain myself. So yes, and if something isn't clear or something like that, please interrupt me if there's something basic that I'm skipping over that you really need to understand. Just let me know. So to give a quick overview first, why do we do radio astronomy? And so to know the story, you're gonna have to think back in high school, or maybe you haven't been there yet. We're gonna talk about the electromagnetic spectrum. So light is not just what we see from, red to purple in the rainbow. It actually goes out further in all directions. And that is what we mean when we talk about the electromagnetic spectrum. What we see here is the visible spectrum is here. If you go more into the red frequencies, you have infrared, you have microwave, and then you go all the way to radio. This is what I study. If you go, though, from purple, you get to ultraviolet, then you get to X-ray, and then you get to gamma ray. And the reason we're interested in all different parts of the electromagnetic spectrum as astronomers is different parts of the electromagnetic spectrum have different kinds of emission from different types of physical processes. So if you're interested in what's happening, basically, you're going to have different parts of your puzzle on what is going on in the physics of your object, or literally what's happening at your source at different parts of the spectrum, and you're going to have to add them all together to figure out what's going on. You're going to see some things in the radio that you're not going to see in the optical, things like that I'm going to tell you a bit about. And so that's why we're interested in basically everything you can see. And this is basically just all the different telescopes we use at all the different wavelengths to study all these different kinds of light from space. The reason it's also very important why we like radio astronomy is the Earth's atmosphere is a huge reason why we study different parts of the electromagnetic spectrum in different ways. So if we're looking here, this is visible light. So if you just had your rainbow, and this is what you have light coming from space. This is the amount of light that's being blocked by our atmosphere. Our atmosphere, as we know, has a lot of oxygen, has a lot of water vapor, things like that. If you have light coming down, it's going to interact with all that stuff before we can see it on the ground. So most of the stuff gets straight down. People know who use the observatory here. You have some wiggling from the atmosphere, just from the air, turbulence. It's called distortion or seeing. that you'll see at an observatory. But that doesn't affect you too much. You go onto a mountaintop high up in Chile or Hawaii or somewhere, and you can probably do your astronomy just fine. Sometimes it's just the same as if you're doing it up in space these days, because we have a lot of great technology for that. There's the shortest wavelengths, so gamma rays, X-rays, ultraviolet, they're all blocked by the upper atmosphere, but so that's good for us. We don't really want to be bombarded by gamma rays and X-rays in our daily lives. But so you're going to have to build a space telescope to look at those. And then we also have a lot of the infrared spectrum is actually blocked by the water vapor in our atmosphere. So you can't really observe those wavelengths unless you do something crazy like fly a plane above the atmosphere, build a space telescope, things like that, usually to study those wavelengths. On the other hand, radio waves, we are not affected at all by this. We can build our radio telescopes on the ground. We don't have to worry about building a huge expensive space mission, things like that. And we can just do our science. We can also do our science during the day. We don't have to wait for night. As long as you're literally not pointing to like within 10 degrees of the sun or so, you're perfectly fine for radio astronomy, and we can just do that during the day and things. So it's very nice for scheduling. So as I said, we have different kinds of sky and things like that. So if you're looking up at night, this is going to shift for me. There we are. So, here we have a Milky Way sky. The amateur astronomers here are the more serious. It's a southern Milky Way sky. We'll talk about why that is in a minute. And, if you went out in the middle of the southern hemisphere, looked up, this is what the sky would roughly look like to your eyes. You would see a Milky Way like that. If we looked in radio waves, though, this is what the sky would look like. And so the radio sky, as I said, different things emit in different frequencies, looks very different to the picture I just showed you before. The first thing to note, we have these splotches here. Those are all supernova remnants, so stars that exploded thousands and thousands of years ago, left behind their remnants, and that's what we're seeing in the radio sky. Most of these dots, though, that you see are not actually stars. Most of the things that we see in the sky, in the radio sky, are what are called active galactic nuclei, which is basically a supermassive black hole at the center of a galaxy. Some dust is falling onto it, and it's giving off a huge amount of radio wavelengths, quasars, things. So basically just our sky is supermassive black holes. They're not usually stars. Stars you'll sometimes see, but they're actually the minority of all the things that you'll see in the radio sky. So that's always, kind of one of those things. We're already going into kind of a different wavelength for what we see in the sky as well. And so as I said, what I do, though, is radio transients. So, we have that radio sky. Most things in that radio sky aren't really going to change too much over time. They're kind of just going to be the same thing, because most stuff in astronomy takes a really long time, thousands or millions of years for any process to happen. I'm not interested in those, though. I'm interested in the things that happen short time scale. So something that can happen, within a few years. So within my lifetime, even most of the things I'm going to talk to you about today are, I think all of the things I'm actually talking to you about today are younger than me. Some are, so new that they've only been known for a few weeks or something like that. So I'm interested in these things that change a lot. And also there's another thing. The reason I like this, I should say, transient radio astronomy, is because basically what I decided in my astronomy career, you can kind of be an expert on one pet subject, or you can be like, I want to be really good at one technique and then be able to study a lot of different things with that technique. That kind of suits my personality better. So I actually did this plot once for some students. I was giving a talk, and it's kind of nice. This is my research view of the sky, and I'm going to explain this. So right ascension RA, the amateurs here know, that's basically what is going overhead. If you had a 24-hour clock, as everything's going overhead, everything will eventually pass overhead. So that's just our coordinate system to say what's in the sky. So this is the spread of the sky. And then this is the distance in light years for how far away things are. And so as you can see, I basically don't do anything in the Milky Way galaxy. These are just some brown dwarfs. We're looking for some natural radio emission for exoplanets. Unfortunately, that's another talk. Distance to the Andromeda galaxy, which is the closest big galaxy to us. Edge of the visible universe. As you can see, I'm optimistic that someday I'll see something beyond the edge of the visible universe. But most of these things are, getting pretty far away. So these stars here, these are all supernovae that I've studied over my years. So basically, it's just anything that I've written a scientific paper on. I threw it on this plot, and I thought it was kind of interesting to me, at least. These are all AGN here, these diamonds. These are all tidal disruption events. So those are starting to get pretty far up. But as you can see, you can really kind of look at different scales, different things, different kinds of radio emission, stuff like that. So, you know, this is maybe a lot to look at. I should mention, by the way, the reason there's a cluster here is it's the Virgo supercluster. That's starting to fill in. So you can actually start, if like you look at some astronomers who have done this over the years, you start seeing like structures fill in, but I'm obviously a little bit further from that still. But to start off, anyway, I'm going to tell you about one thing here that I've been studying a lot in my career, which I really like because it's near and dear to my heart, which is Supernova 1987A. And the reason we're going to talk about Supernova 1987A is it's the closest supernova explosion that happened to us since the invention of the telescope. And I'm going to tell you guys a bit about why Supernova 1987A is important, what we saw, everything like that. But first, I'm going to tell people who aren't familiar the story of how a star lives and dies. So the evolution of stars, there's two kinds of main tracks you can take. Everybody starts off in a cloud of dust called a nebula, and the gas gets squished, and then basically, eventually, a star is born. If you're a star that is a smaller star like the size of our sun, you first, you know, you're a star, you're living billions of years, you're fusing hydrogen into helium in your core, that is how you shine. Eventually, the star gets bigger, and it's going to kind of swell out. It's eventually going to poof its outer layer out. It's going to be called a planetary nebula and leave behind something called a white dwarf. So that is most of the stars in the universe. If you're less than 8 times the mass of the sun, that is the life you lead as a star. However, about 1% of stars in the universe are more than 8 times the mass of the sun. And then you go on this large star track. So what happens when you're on the large star track is, you know, you're still burning hydrogen into helium and things like that. You're going to swell into a red supergiant, so it would be a lot bigger. And then you're going to have a supernova explosion. So at the end of your life, when you're no longer able to fuse hydrogen into helium, you can't fight that gravity anymore. You're going to have a giant explosion that's left at the end. You're going to leave behind either two objects, either a neutron star or a black hole. A neutron star is basically maybe about 10 miles across. It's literally just a ball of neutrons. It'll weigh as much as a normal star, but as I said, only be like maybe 10 miles across. A black hole is going to be something that is so dense that light can't escape its surface. And so, you know, the thing to remember here really is that the large stars, the supermassive stars in our universe are really kind of the rock stars of the universe. So they're basically very big, they shine bright, and they also die very young in fiery explosions. So when we're thinking of a supernova explosion, this is roughly what happens. As I said, the hydrogen is no longer fusing into helium, it's run out of fuel. It is going to explode like this. It's going to send out a giant shock wave. And it's also going to be so bright, one supernova can outshine the rest of the galaxy around it. That does not look very nice, does it? Let's play it again. And the thing to notice here, though, is also when the supernova explodes, it doesn't just, you know, it sends out this giant shock wave, which is almost traveling at the speed of light, is how fast these things go. And that is going to go and it's going to interact with everything around it. And that's going to be very important later. And the thing that's really cool about supernova is, I should say, like, we've been studying these as humans for a very long time. It turns out we are actually, you know, our ancestors have studied supernovae. So for one example here, like something that our ancestors looked at was a supernova called that occurred in 1054 AD, so almost 1,000 years ago. This supernova exploded, and we know it's there because we know it happened because it was recorded as a guest star by the Chinese, who are very good astronomers. We know that the Japanese and Arabian astronomers also saw it. We think the Europeans saw it. So this is a Chinese record here of this guest star that occurred in the sky, the Europeans. And this is actually in Chaco Canyon in what is now New Mexico. We think Native American astronomers also saw this because apparently this is the supernova. This is the size of your hand, and this is the rough orientation of the crescent moon on the day that coincides with this Chinese record. So it looks like everybody around the sky saw this very bright star. The records tell us it was so bright that it was basically, you could see it in the day for a month, like just in the daytime sky. It was so bright you could read by it at night. And it was in the sky for almost 2 years before it faded from naked eye visibility. This is an incredibly huge explosion. The thing that's also really cool, though, is so these Chinese astronomers, they're so good that they told us where in the sky this guest star occurred. And these days, you know, with big, powerful telescopes, astronomers went and looked, and they saw this. So this is the Crab Nebula, which to me looks like a giant explosion happened there, right? And so this is basically 10 light years across. So when we say light year, we mean the distance it takes for light to travel, which is the fastest thing in the universe, in 1 year. So it has clearly expanded over 1,000 years or so into this giant mess called the Crab Nebula, and astronomers still study this today. It's one of the closest supernova remnants we have to us. But the thing is, so, you know, supernovae happen. We have seen them with our eyes and everything like that, which is very cool, but they're also not that common. So what a supernova in a galaxy of our size, like the Milky Way here, we estimate one happens about every century, or 50 to 100 years is what they say, or 1 or 2 a century. So the last one that we have seen, though, was called Kepler's supernova, which occurred in 1604. So Galileo saw it, but he didn't have his telescope yet. That's kind of the times we're talking about. Well, you can ask, okay, you just told me that you should see a supernova every 100 years. What's going on? That's been 400 years. It turns out, you know, you can see all this dust here in our Milky Way. The dust in our Milky Way really obscures so much of the galaxy that probably supernova have happened, and astronomers have found potential remnants that they think are younger with other wavelengths. But that light probably never reached Earth. So, you know, the astronomers of the 1700s or 1800s didn't see these things. Another way to think of it, if you're thinking of the Milky Way, and we can basically see if the Milky Way was the size of the United States, it's basically about the distance of the state of Virginia. So, you know, you can see a small part, but eventually this dust becomes a problem. However, so the closest supernova that we've seen, you know, since 1604, occurred not in the Milky Way galaxy here, but in this guy here. So these are the large and small Magellanic Clouds. These are satellite galaxies of the Milky Way. They're about 170,000 light years from us. So 170,000 years for that light to travel from that galaxy to us. And they're kind of, you know, like a few percent the size of our Milky Way galaxy. And if you're going to go, if you zoom in on this large Magellanic Cloud, you see this. This is called the Tarantula Nebula. It is the biggest star-forming region that we know of in our local universe. It is about at least 10 times the size of Orion. I can't quite remember, but it's basically just this gigantic star-forming region where stars are being born, you know, every day, every year. And the interesting thing is also a lot of the biggest stars that we know of are in this Tarantula Nebula. The reason that is because, as I said, there's a lot of dust in our Milky Way. If you're looking for the biggest stars in the universe, we have a direct line of sight toward this large Magellanic Cloud and this Tarantula Nebula. So if you're, you know, somebody who's contracted by Guinness to go find the biggest stars in the universe and like write down what they are, I can assure you pretty much all of them are in this area, it turns out, of the sky. Not that there aren't probably bigger ones in our own Milky Way, we just can't see them as easily. And as I said, though, if you have big stars, you know, forming in one region, well, what ended up happening in 1987 on the edge of the Tarantula Nebula was a very important event called Supernova 1987A. So what happened was, in 1987, on February 24th, there was a University of Toronto astronomer named Ian Shelton, and I spent some of my time at University of Toronto during my PhD, so I'm, you know, obliged to tell this story. And he was observing on one of the telescopes in Chile in an observatory down there. And he was having trouble with the clouds or the weather or the instrumentation. I don't remember. No, it wasn't the clouds, because this wouldn't make sense then. He was having trouble with the instrument. And he kind of decided around 3 a.m., this isn't going to work. I'm just going to turn in and try again tomorrow night. But before he went to bed, he developed his plates. So for the young people, it used to be in astronomy, you didn't just take pictures with your computer before computers. You exposed on these giant glass plates, basically. And that's how you did astronomy. So he's like, I'm going to do my data reduction before I go to bed, which was a good lesson because he looked out and he was imaging the Large Magellanic Cloud as part of his experiment. And he's like, there's a really bright star there. That star is so bright, I think if I went outside, I'd be able to see it with my own eye. And he went out and he looked up and he saw it. And there was another astronomer, a Chilean astronomer, who also was working there that night. And Ian was like, do you see this? And they realized that they were seeing a supernova for the first time with their own eyes, the first one a human had seen in about 400 years. My understanding is because this is 1987, the satellite, or it was this, whatever phone they had wasn't working, and they had to drive like 100 kilometers to basically put in a telegraph to say that we found a supernova, like, you know, to the people. So that's how they got credited for discovering the first supernova. And it's a good thing they did, because it turns out several other astronomers were observing that night, but they did not develop their plates, and they only like woke up the next day. They were too late. Ian was first, so he gets the credit and all the glory. But anyway, Supernova 1987A, it was a very exciting thing. Like, my advisor, who's Australian, said he went out in suburban Sydney as a 13-year-old and saw it with his own eyes. So, you know, this was bright enough for a few weeks. You could see it from the southern hemisphere. And it was kind of a weird supernova. So the first thing here, it was very important, was this is the first time in history we saw the star that exploded, because this is a very well-studied nearby area of the sky. And they were like, oh, that's the star, and there's the supernova. So, you know, that was very helpful for a lot of modeling. The second thing that was very important was it was the first detection from outside the solar system of a bunch of particles called neutrinos. So neutrinos are fundamental particles like electrons or something like that, but they're kind of weird. They're very light. They don't have very much mass. They don't really interact with you, and they're just everywhere. And like, there's a lot of them everywhere. So to give you an idea about neutrinos, I just remembered my favorite part about doing this talk in person. Everybody has to give me a thumbs up. Yeah, this is great. Okay. So every single time, every second, about 100 billion neutrinos are streaming through the tip of your thumb there. So this has been happening all of your life. Obviously, it hasn't affected you, but there's just a lot of neutrinos everywhere. The problem is, as I said, though, they're very hard to detect. So this is actually, for example, a neutrino detector in Japan. And to give you an idea, so this is basically normally completely filled with water. And this is so huge that this here is 2 men in a boat, to give you a sense of scale. And all these little balls here are basically detectors. Normally when this is filled with water, if a neutrino particle streams through, it'll give off a faint flash of light. And that's what these guys are looking for. It's called astroparticle physics. It's very, very hard to do. In 1987, though, 3 neutrino detectors around the world detected, I believe it was 18 neutrinos within a second of each other. And they realized, because it was the same day Supernova 1987A was discovered, that was actually light, or neutrinos, that were created in the supernova explosion 1987A that escaped and were from that. When you have a supernova explosion happen, you get as many neutrinos as there are atoms in the sun created. So even though this was pretty far away, they still detected these neutrinos, and it was a very exciting moment for neutrino physics. The other thing I should mention, this also made people realize that if we had another supernova that occurs in our own galaxy, you would actually have neutrinos that suddenly all the neutrino detectors on Earth would go haywire. And you can actually sign up for these alerts. So, you know, like if you want to go learn about the next neutrino alert from supernova, you can go and sign up. Anybody can do it. Anyway, so Supernova 1987A is a pretty cool, exciting moment. Hubble was not yet launched, but once it did launch, it took a closer look, and it took this picture, which I'm sure many of you guys have seen before. We have, you know, these are just foreground stars. These aren't stars associated with it, but we have this complex ring structure, which I'm going to show this illustration because I think it shows it better. So this is basically what we saw in that earlier picture. And what we're seeing is this is the innermost supernova remnant. And we actually have, this is an hourglass figure. Like here, it's just from our orientation, this is what those rings look like. So what we have is we have this innermost ring of gas. We have these outer bits of gas, and we think these are basically giant mass loss periods before the star died, in the roughly tens of thousands of years before the star died. It turns out when stars are pretty close to the end of their lives, they just kind of shed out a lot of gas and dust and things like that. They're already pretty unstable by the time the final explosion happened. But anyway, so as I said, you know, this supernova happened, and what happened is the shockwave went out, and it's going outward, and it's interacting with all this gas, and that's kind of what we've been doing. So when I describe, okay, 1987A supernova 1987A happened, you know, this is what this looked like. So what we're doing, this is me in 1987.
Oh my God.
Yeah, I told with this audience this would be interesting to show off, but yes, I was 1 year old. But you could imagine, you know, if you were an alien anthropologist and you came to Earth, then what would you do if you want to understand how humans grow? You might follow one human and, you know, say, okay, they started small and they were little and cute, and then they got bigger and less cute, and how did this happen? And so that's really kind of what we're doing with supernovae. So supernova 1987A happened in 1987. Since then, astronomers have basically been studying it at all wavelengths, being like, what happened? How did it grow? How did it expand? How is it turning into a supernova remnant? That's really what we're doing. So for supernova 1987A, it's in the southern hemisphere. So we, of course, can't use our telescopes in the northern hemisphere. Instead, use this, it's called the Australia Telescope Compact Array. So these radio telescopes, this is a railroad track that they're on, and you're kind of moving them because there's different kinds of observations you want to make. Sometimes you want your track longer or shorter, your baseline. And this is what I basically used to study supernova 1987A. It started to become radio bright in around 1991, 1992. And then basically since it's been there, we've been observing it to see what is going on. And this was part of my PhD thesis. And, you know, if you have observations that span so long, well, of course, you're going to make a movie. So we're going to watch this movie. And what you can basically see here is, you know, it looks like a smoke ring, right? So this is, as I said, that shock wave is going outward. And as that shock wave is going outward, it is interacting with the gas around it. And it is going to light up in radio. In radio, what we're studying is electrons, if there's magnetic fields and they're spiraling in magnetic fields, that's what we're studying. For anybody who's more scientific, we're studying synchrotron emission is what it's called. But so what we can see here in particular here is around 2003, it starts to light up a lot more dramatically. And what happens is I showed you that innermost ring of dust in that picture. We think that looks like when, if you look at the Hubble images that have been taken, when that shockwave hit that innermost ring is basically when you start seeing this light up. And this is what I was studying in my thesis was 2013 to 2017. And that was basically the period it left, this shockwave left. And you could actually even see, like, studying the velocity of the thing, how it actually slowed down when it hit this dense bit of gas and re-accelerated after. So it was pretty exciting. Another way to show it is I could just show you all these pictures individually. So I do cross stitch as like a hobby. This is cross stitch supernova 1987A. And so basically this is the exact same data. This is like 1992 going over time. And then this is the most recent one. So the nice thing is it's all pixels, right? If it's on your computer, which is basically what this is. So this is the most recent one. You can see this is actually accurate to coordinate scale. This is the resolution we have in radio astronomy. It's called your B model. And yeah, so this is another way of showing what exactly is going on in supernova 1987A, what we're doing. You can also start to see a lot of things. So like the brightness is not equal in all directions. Does that mean the density around it is different? Or does that mean maybe the explosion was not the same in all directions when it originally occurred? So there's all these questions about how this supernova is changing over time, how it's interacting with its surroundings, things like that. So I'm just going to wrap up for 1987A by asking really quick, what's at the center of 1987A? Because a lot of people ask this. And so we don't know yet. There is evidence, though, for something called a pulsar wind nebula. So this is not the center of 1987A. We don't really have a good picture for that yet. But what happens if you have one of those neutron stars and there's a bunch of gas around it, it's going to start interacting with that. And you're starting to have the first reports from people who are like, our measurements are consistent with this. Of course, you have other people who are like, I don't think this is consistent with it. But often a lot of science is like, you keep adding a little bit more evidence every time. I think eventually, I don't think anybody's going to be shocked that, okay, we finally found the pulsar wind nebula. It's just the question of how much evidence you need as a scientist until you get to that point. So that is supernova 1987A. I also like to always start talks with this because you can actually see what's going on. The rest, everything else is so far away, you only see like a little point source and you have to trust me for what's going on. So what I'm also going to talk to you about is tidal disruption events. So these things that are like the big fat diamonds here, these are all what are called, thank you, Ladybug, all tidal disruption events. So as I said, these are when black holes shred stars. So how does this work? I found a very cool video and I'm going to talk to you about it. So you have a supermassive black hole. This is what they look like. We have that beautiful picture of what a black hole looks like. So that's, we assume they're all roughly similar. And we have a star that's going to have a very bad day, which is this guy over here. And so what happens is for whatever reason, the star is on an orbit and it's going to go too close in its orbit to the supermassive black hole. So as it happens, it's going to go forward. It's going to start stretching. It's called spaghettification as the black hole's gravity. This is a scientific term, guys. And then eventually, though, as you can see, it starts basically getting shredded apart. The shredding apart part is just a few hours. And basically about half the mass of the black is going to fall into the black hole and like an accretion. It's about half the mass is going to go in outflows, either creating some jets or, you know, just normal outflows that are less structured, things like that. But that is basically what's happening when a tidal disruption event happens, as far as we can tell. And, you know, these things will become incredibly luminous, more luminous than a supernova explosion. And you basically are looking for these events to learn about the supermassive black hole and what is around it. So my research on these is, as I said, in the radio. And we're using telescopes like the VLA in New Mexico. These are my bread and butter as a radio astronomer. And what happens though is, as I said, there's these outflows that happen from the tidal disruption event. And these are basically just going to go outward like that shockwave from supernova 1987A and slam into everything surrounding it. And what's going to happen there is it's going to slam into everything surrounding the supermassive black hole. And you're going to also, from the radio observations of this, learn a lot about that outflow. So its radius, its energy, the magnetic fields that are involved, even the density of material this wave is slamming into. We can learn all these things just from studying them in radio. And then, of course, we're trying to use this information to piece back what exactly, what exactly the system is like, how things like that. I should also say at this point that, so I'm going to tell you, we don't have that many of these yet. This is still a very new field. It's only been around for a few years. So we have about 30 events where radio telescopes, or 30 published events where radio telescopes went and looked. And of those, you have about 10 that were detected. So, you know, like in the first immediate time after. So this is still, you know, a small numbers field, but it's still very exciting to figure out what exactly is going around these things. So to give you an example, like I'm going to tell you guys about two tidal disruption events that I've studied in detail. The first is called Swift J1644 plus 57, which really rolls off the tongue. It's basically, so the way these things are named, if you're ever like, why do astronomers have such terrible names? Swift is the satellite that discovered it. 1644 plus 57 are the coordinates of this object. So that's all the numbers and things mean. So it was first detected, as I said, by the Swift satellite, March 28, 2011. So only about 10 years ago, in astronomy, that's like, you know, nothing. 3.5 billion light years away, so like incredibly far. So Swift detects these very bright flashes called gamma ray bursts that some supermassive stars give off when they die in supernova explosions. And these usually last a few seconds or a few minutes tops. So it just detected this gamma ray burst flash and it just kept going. It just didn't stop. And everybody was like, oh, okay, we have something completely different on our hands. It turns out if we, you know, as I said, everybody looked with every single wavelength that they had and you added together all the pieces. It turns out when this tidal disruption event happened, it wasn't just that the star got ripped apart. It also launched relativistic jets. So basically jets of material traveling at many fractions the speed of light. So I think there were like 70% the speed of light or something crazy like that, which it should be noted, people had theoretically thought tidal disruption events might happen. Nobody predicted you might get relativistic jets from them. The other thing that was really crazy was, okay, this relativistic jet got launched. It was very exciting. After about a year and a half, the data showed that the jet had turned off. So basically like the X-ray radiation plummeted, all these different things. And I mean, normally these relativistic jets, we don't really understand how they get created. And normally they last, you know, thousands or even millions of years. So the idea, like a year and a half, like that's a postdoc, right? You know, like this is a very cool data set, very contained. It's been very useful for people trying to understand how these jets happen. And I should mention that, yeah, the radio emission though, just because the jet turned off, you know, that shockwave is still going out, it's still interacting. And we still like to check up on a Swift J1644 plus 57 and see what's going on. So, you know, another cross stitch, because this is what I do. It's been a long pandemic, guys. So this is what a radio image looks like for something that is 3.5 billion light years away. So you're not going to see like the nice circle and, you know, kind of see it going outward. You're just basically going to see your point source and you are going to go and measure the flux of how bright it is. And then you're going to do this at multiple frequencies, and then you're going to fit a theoretical model that a very intelligent astronomer figured out and you think is valid physically for the physics. And this is basically what we do. We look at these things and then we're fitting models to try to figure out what exactly is going on in these systems. To give you another example of a tidal disruption event, this is a non-relativistic tidal disruption. It did not launch a jet or anything like that. So this is one called AT 2019 DSG. So it was the most luminous optical one detected to date. So it was only 30 million light years away. So, you know, this is like relatively next door, right? Compared to 3.5 billion light years away. And, 750 million, still, that's next door. Yeah. So what ended up happening though for this one is because it was so bright and optical, usually what we're doing is somebody discovers one in optical and we're following up on radio. We're usually not discovering these tidal disruption events there initially. Then we threw the VLA at it, we observed it, we looked at it with the ALMA, which is a radio telescope in the southern hemisphere. That's basically, we're normally looking around 6 gigahertz, this is 100 gigahertz, so we could really fit the spectrum much better than anything else we've seen to date. And to kind of give you an idea of why AT 2019 DSG is important, you can actually start, as I said, studying different parameters for these. And this is, so if we're talking about the density surrounding this tidal disruption event, and you can start comparing them to other objects around us. So this is just distance from the black hole, and this is the density, so in centimeters cubed. So if you're saying 1 centimeter, 1 atom in each centimeter of empty space, most space is not completely empty, especially around black holes. They're kind of messy eaters, it turns out. And you can see here's AT 2019 DSG, and you can really start seeing the density around this. You can compare it to our own Milky Way galaxy, so Sag-A star. This blue line here, this is the density if you were looking around our black hole in the center of our Milky Way. The thing that astounds me whenever I look at these is we actually know the density around these supermassive black holes, millions or even billions of light years away, far better than we know for our own Milky Way, just because it's dusty, it's a little more complicated of a measurement to make, but I think that's absolutely fascinating. If you want to know how these things work, this is what you're looking at now, are these tidal disruption events. We can also, of course, do the same for the relativistic ones with J1644 plus 57. We can see it's a lot more steep. We can see it's similar to M87, so that's the black hole they took the picture of. Does that mean much that it's like very similar to that one? That's a very supermassive black hole. Obviously, you know, we're kind of missing, as I said, this is a very new field, some data points.
The distance scale, is that in light years at the bottom?
So that's actually, no, it's divided by Schwarzschild radius. So this is like, I just put a simpler one. So basically, because all the supermassive black holes are very different in size, we divide by the size to kind of make it a more universal scale. But that becomes complicated in public talk. So let's just say distance.
You can thank me for asking later.
Oh, yeah, sure. Anyway, the other thing we can do is kind of look at the energy and velocity of these guys. And what's interesting is we're starting to see there's interesting, like, there's 2 kinds of populations here. So this here is velocity. This is also slightly more complicated velocity for you.
I won't ask.
But the important thing here is this is the line between if something is relativistic and non-relativistic. So is it 10% the speed of light and up? I think is where we put that line. And this is the energy, so how much energy a system has. And what you can see here is, you know, we have this nice clump here that they're all kind of hanging out together. We've also overlaid here, so this is typical speed, so from a supernova 1987A or something like that, just normal supernova, you know, speeds and velocities that you'll see from the, and energies that you'll see. But then up here, so we have Swift J1644 57. Interestingly, in the evolution, it goes this way, it doesn't go this way, so it's slowing down over time, right? It's no longer relativistic, things like that. And these are the gamma ray bursts that I was telling you about. So those very energetic, very fast events. And what you can see is like, that is just a very different category from the guys down here. So what's going on? So the interesting thing is, I should mention, so Swift J1644 plus 57 happened March 2011. Everyone was very excited. This second event happened, and then that was later in 2011. Everybody was super excited. Somebody discovered a year or 2 later in archival data, a third one from 2011. Oh, this is all Swift data. Everybody's incredibly excited. We have not seen a relativistic jetted tidal disruption event since 2011 when we saw 3. So if you're an astronomer, you're like, okay, well, you know, I checked, you can't order these on Amazon. You're just at the mercy of what the universe is sending you. So you can just kind of say, well, okay, the Swift satellite's been up for 15 years. We've seen this many other tidal disruption events. We think maybe 1% of them shoot off these relativistic jets. Is that like a hard and true limit? No, this is, you know, as I said, evolving science. I will tell you, like, everybody has a trigger set aside on all these instruments. So like, if a jetted TDE gets discovered, like we're moving the VLA like as fast as humanly possible to go look at it. So we're waiting. It's just, it turns out it's a very long wait if you want another one of these. So as I said, it looks like there's 2 populations, but in the past month-ish, I've actually become concerned or interested. I think there might be a 3rd. So this is kind of one of those where I was thinking, should I talk about it, should I not? But I think this is really exciting, so I'm going to talk about it. So this past year, there's been 2 of these TDEs reported where they got very low radio limits, like swung immediately when the optical people saw it, saw no radio emission from them. And now, like years later, they're like, oh, we think we see radio emission. So that's pretty wild. And they don't really know from that data what is causing it. We just see that the radio is going brighter later, and there's several things that could cause it. From their data set, you can't really tell. So of course, what is the solution to finding something, figuring out something like that? You actually then, of course, throw your own radio telescopes at TDEs with your own campaigns and see what you can find. So I'm part of 2 proposals here where I've been reducing the data and everything like that. There's 2 called, one is the Very Large Array, and this is Meerkat, which is a new radio telescope in South Africa. By the way, I really like the name Meerkat because, of course, we think of the animal. It was originally the Karoo Array telescope, and it was going to be 20 antennas, but then the budget increased so they could build 64 antennas. So now it's Meerkat because more cat, yeah, anyway. I thought that was great, but anyway. So we threw Meerkat at some of these late time TDEs. I think we got detections on all but one of them. So that was pretty cool. And then we're like, okay, let's go with the VLA at some of the better studied ones. Oh, look, as I said, this is what something looks like if you looked, didn't see anything, and this is what our point sources look like in radio emission. So this is one called PS16DTM. I know they all have great names. These are all the surveys that discovered them, and then this is the year, and then just you go through the alphabet. Supernova 1987A was the first. Now we're at 3 or even 4 letters in these. So nobody saw anything in 2016. They looked really carefully, 2 to 5 months. This is one of my collaborators, so I know she did a good job. We looked again at some data from 2021, and yeah, as I said, there it is. And preliminarily, the data we have, it looks like that outflow is 2,700 kilometers a second, which I know sounds incredibly fast, but that's actually very similar, if not slower, to what I was showing you at the end of for Supernova 1987A. That's not a very fast outflow. Does that relate? Well, we're not quite sure. We probably need more. And then, oh yeah, look, I reduced another data set here. And then this is, I think this was, 2 or 3 weeks ago, just 2 or 3 weeks ago. This is a TDE, 2018 HYZ, seen in November 2018. Also, don't take a picture and put this on Twitter, please. Obviously, this is still new and exciting stuff, but it needs to be published. So we, in 2018, this TDE happened. People looked with Amy, Alma, deep limits, consistently nothing. There's a VLA sky survey, didn't see anything. Okay, there was no radio emission. Then what we see, we looked in June this past year. We had some time, as I said, of our observing campaign, and we have a detection here. So these 2 data points here, as I said, there's a VLA sky survey. They go every 18 months or so looking. Definitely didn't see anything, and suddenly it's there. So basically within about 9 months, it suddenly brightened about 4 times. The unfortunate thing is we only got data at 1 frequency, and if you're only getting data at 1 frequency, you usually need a lot of frequencies to be able to do this modeling that I was telling you about to figure out what's going on. So we actually had to submit what's called a DDT, Director's Discretionary Time. So everybody always wants to know in astronomy, what happens if you've made a new discovery? Like, how do you follow up on that and things like that? And the answer is, you have to write a proposal as fast as humanly possible and be like, please, this is really important. I cannot wait for another 9 months or a year until you would go look at my object through the normal means. So we did it, and it got accepted last week, and we are in the observing queue for the VLA. We're still waiting for them to look at it because I did not get the highest level of priority because this thing is probably not going to disappear on us, but who knows? So anyway, that's been kind of, the excitement of being an astronomer, I think, is when you find something new that nobody else on Earth knows, and, then you can start sharing it with other people, like the nice people in Rhode Island who invited you to give a talk. And I should mention, this is only two of about 35 TDEs in our sample. I assure you most of them are not this exciting, but I think this is exciting enough that, you know, it's going to keep me busy for the next little while. So that's kind of the research I do. So just to wrap up, I hope I convinced you guys that radio astronomy is a very powerful tool for understanding all these transients near and far. For supernova 1987A, we can see that, you know, there's a shock wave, it's re-accelerating as it leaves a gas ring, things like that. TDEs, we can also learn a lot about their properties, such as their radius, their energy, their density, all sorts of things. And finally, to wrap up, as Steve said at the beginning, if you want to learn more, I was a little frustrated because I didn't think there was a good article about TDEs for the general public. So I wrote one, and it's actually in the December issue that's out right now for Astronomy Magazine. Yes, thank you, thank you. Yeah, so please go read that or just ask me any questions you might have if you want to learn more about these objects. And thank you very much. So I personally haven't, but my group has that I'm in. So the group I'm in, we have like, we're just interested in all transients and all different wavelengths and things like that. And what we have time for are if a neutron star merger is detected, so it's called a kilonova, then we are one of 3 groups that are allowed to trigger with James Webb Space Telescope when it launches. We all have different criteria for what we're allowed to trigger on, so that's how it's kind of made fair, I guess. But so pretty excited about that when it gets up.
I have a question on scheduling observing time. We've been to the VLA and we know how long it takes to reposition everything.
Mm-hmm.
You said that you have Meerkat or VLA on alert that if you do something that you get priority. Does that bump the people who are already observing? I mean, how does that work?
Yeah, great question. So it depends on the observatory. For the VLA in specific, so they have 2 regular calls for proposals. So it's February 1st, August 1st, so I'm always busy then. But basically you're going to submit, and if it's something like this, you're like, I just need, you know, it's going to be 3 hours of time or however much time, and just give me a trigger is what it's called. So it's not for a specific object. It's in the observing queue, so we're not the ones taking the observations. It's remote observing, even pre-pandemic. And then whoever's observing, it's basically, there's different priority classes. So then they're going to be like, oh, that's an A priority. I'm going to observe that now. So they will eventually get to it during the semester if it's like, oh, there would have been somebody else observed. So that is taken into account for the timing. And then so for the special time I got for this most recent project, there's like less than 5% of all observing time will be for that. So it's not that we're kicking out somebody and they're not getting their time. It's slightly nicer and kinder for our kind of astronomy.
So the priority means you might be able to observe within the next month, as opposed to waiting for 9 months. It's not like an instantaneous thing where in 3 days.
If you make the case that you need it done in the next few days, then they will do it. As I said, that the problem is, so for something where it's like we saw it in June and it's like 3 years, like it's probably not changing that fast. So it's like, I mean, I'll be surprised if I don't get that observation within the next week. So 2 weeks after I put in, that's pretty good.
Does a committee review that?
Yeah, so that's normally, so there's a telescope allocation committee is what it's called. So that's if you're going through the normal cycle. So I'm actually on it for the transients the next time around. Obviously nothing for anybody who I personally collaborate with. But then for something like I need the special trigger because I didn't realize I'd need to look at this object again, then that is the observatory staff themselves are the ones who make that call. But those are like pretty, like it's hard to get that time. You have to really make a case if you're not going through the normal channel. So.
I just want to make a comment. For optical telescopes, you do get bumped off.
Yeah.
So we do occasionally lose time, and then they'll just, you know, it's assumed that when you're given time, if there's something that's high priority, you'll lose a small fraction of it.
Yeah.
Do you lose it or do they just move it forward?
Yeah, it depends on which telescope, because I know, so like Harvard, our telescope, we were like on Magellan, so we were granted for gravitational wave follow-up 2 nights. We didn't have enough this most recent run to fill that, so then it was just like, okay, well, like, you know, somebody else could use it. But the problem is some objects, if you know, you only have a certain amount of time, you can see it in the sky. Radio astronomy don't usually run into that problem. All we care about is where the sun is, so that's usually okay.
You said director's discretionary time. Do they, in optical and radio, do they, is there little segments that are?
Yeah,
Every telescope that I'm aware of has this, just because, I mean, you don't want if the next galactic supernova goes off, no way for people to like, observe it, right? Like that would be heinous. Also, like, as I said, for the VLA, at least there's like different levels of priority. So there's also just a lot of filler time. That's actually pretty easy to get. So like I had a student I worked with last summer. He found something that might've been interesting in the survey catalog. So we put in and we actually got one of these filler time observations. So it was just like, oh, a half hour, nothing's going on toward the end of the, observation. It's getting a little empty in the queue. So, that can happen. I should also mention it's very nice. The VLA, technically anybody can apply, like high school students have even gotten time using the VLA. And that's very nice because then, say Australia, their telescope, they're also open sky. So I can just go put in a proposal as an American astronomer to use that. So that's kind of a nice thing in radio astronomy in particular, we tend to be.
I have a question from Bob Napier. How does the increase in artificial satellites affect radio astronomy? Optical astronomy is very concerned with the hundreds of thousands of such satellites affecting their observations.
Yeah, so it's even worse for radio astronomy, is actually the answer.
Yeah.
Because optical astronomy, they eventually go higher up, and then, there's still a problem if you're a major telescope, but they're not as big a problem. Radio, it's basically going to be at 10 gigahertz for Starlink, at least, is what they downlink at. And then once that's, you're just going to lose that frequency. So I can't do this modeling as well. I should say, so there was a big report that came out this week called the Tidal Survey. So every 10 years, astronomers get together and agree on our space policy for the next decade, at least. So what big instruments and stuff. Mega satellite, or these big constellations, are actually highlighted as one of the biggest problems right now in astronomy that we need to be very proactive at. I think there are solutions, it should be said, like, so for radio astronomy, my understanding, you could just not beam, like, there's a radio telescope there or something like that, but you really kind of need the cloud and arguing to make sure people know that's a problem that they need to solve going forward. So I'm hoping it's, not the end of terrestrial radio astronomy, because that would be very sad, but it is a concern.
You said that with a tidal disruption event, when a star interacts with a black hole, it gets disrupted within like an hour and a half or so?
A few hours.
A few hours.
Yeah.
Huh.
So that's basically just like how long does it take for the fusion to no longer happen? Because a star needs to have a certain amount of density, right, for fusion to happen. And it turns out it's just once you're polling it and everything like that, once a few hours, you're done.
Can you learn anything about the mass of the star from?
You can from optical data. Most of these, like, we've never found, say, a supermassive star that's getting disrupted. But as I said, those are a very small fraction. Most of these stars are less massive than the sun. So like Swift J1644 plus 57, that was like, I think, much less than the mass of the sun. I think it was like half the solar mass or something like that, and still created this huge relativistic jet. So.
Other questions?
You mentioned your use of the VLA and Meerkat. Has any of your research been impacted by the loss of Arecibo?
Could you repeat the question?
Yeah, sure. So the question was my research affected by the loss of Arecibo? The answer is no. Because I basically make radio pictures, as you can see, is what I do. And Arecibo was not doing that. They're looking for pulses, or they were shooting a beam off. It's really the planetary science people have been very affected, because they were like looking at asteroids and stuff, and pulsar timing is the huge problem. I will say, though, I was very lucky. So we actually went to when we got married, and saw Arecibo on the honeymoon. So yeah, I did manage to see Arecibo, so that was good, but not as my capacity as an astronomer. So yeah.
No more other questions? All right, well, thank you very much. I really appreciate it. Thank you all for coming.